Hello there, fellow Calculus 3 students. My name is Braden Monson, and in case you didn't notice, I'm actually in your Calculus 3 class. I know it's a miracle, and I'm very quiet. I can't believe anybody noticed I was there at all. Anyway, today I'm going to be giving you my pitch for how we can take over the world using the power of Lagrangian points. So listen up. First of all, Lagrange, no one quite knows how it's pronounced. I tried to ask Mr. Lagrange himself, but he was unavailable for comment because he is dead. Fun fact about Lagrange, though, he likes taking credit for things that he did not discover. For example, Lagrangian points were actually found by Mr. Euler, or rather Mr. Euler, depending on your pronunciation. He discovered the first three, and Lagrange discovered the last two. That's beside the point, however. Lagrangian points exist between any two orbiting bodies. There are these three, which are guaranteed to exist, and these two, which will only exist if the masses have a difference of 25 times. They are points in space where the gravitational and centripetal and other forces between the two orbiting bodies add to zero. Or rather, if you want to be politically correct, they cancel each other out. And because of this, they are able to stay directly behind the orbiting object, with this having the same period. In this example, between the Sun and the Earth has a period of 365.25 days. And any of the things in these points would also have the same period. That's a little bit weird, but it's also very cool. Now, some of you may be wondering, Braden, why are you teaching us this? I'm exhausted, finals are done, and I was up until 9:30 in the morning working on my project. I'm not even listening to a word you're saying. To which I say, Marty, why are you being so rude to me? I thought we were friends. But again, let me get to this. This is how we're going to take over the world. There are many uses. For one thing, if we look back here, the James Webb Space Telescope is right here. It stays there because it wants to stay out of the sun so it can get better pictures. But if you'll notice over here at L3, it's actually behind the sun, meaning that our technology can't actually detect it. There could be an alien invasion right over there, right now, planning, and we would have no idea. And that is where my plan comes in. But anyways, enough about this. Let's talk about how we can actually calculate Lagrangian.
So, what we're dealing with here is known as the three-body problem in physics. Now, three-body problems are generally quite complicated. They measure how the gravitational forces between three different objects affect each other. However, thankfully in this example, we only need to deal with two because the third object, which would hypothetically be a satellite or a telescope of some kind, it has such negligible force that we don't need to worry about it. Instead, we just need to think about mass 1, the Sun, and mass 2, the Earth. Now, to do these problems, we have to have all of these equations, and we just don't have time for that. So I'm not going to go into this right now. But regardless, to interpret this a little bit for you, we have here the gravitational force of the Sun and the gravitational force of the Earth. And what we want to know is when these forces cancel each other out or add to zero. And as you might imagine, the best way to do that is to take the derivative of it. But one problem here is that these equations are both with respect to time. And for math reasons, when you take the derivative of this, you're able to convert it to be in terms of distance rather than in terms of time. When you take the second derivative of it, I believe is what that says. And from there, you can find exactly when those forces are going to end up canceling each other out or adding to zero. But there are multiple forces that are acting on this at any given time. We also have the Coriolis force, and we have the centripetal forces. Now, what this measures is the amount of force in joules, what these two are. And what you might know about joules is it is a measure of kilograms per meter per second. If we take these derivatives, I believe with respect to the masses, with respect to the kilograms, then we are able to find a gradient. And then all we need to do is solve for velocity. I'm sorry the annotation isn't more explicit about what exactly is happening, but this is the best I have. But suffice it to say that if we take the gradient of it and then we find the extrema points of the gradient, then we are able to calculate exactly when the velocity equals 0, and we get, in fact, L1, L2, L3, which are our 3 Lagrangian points. Now the alpha here is in reference to the percentage mass force of Earth, and the beta, which is actually not in here but was used in earlier portions of this equation, is with respect to the percentage mass force of the gravitational percentage force, I guess, I'm not quite sure how to say it, of the sun. And we find that they are at these 3 points. Now L3 is actually negative. That's because L3 is actually this point on the other side of the sun, which is a little bit bonkers. Now I think I mentioned this, but this is how we're going to overtake the world. We are going to build an alien force over here, and then Earth will have no idea what hit them because our satellites can't actually get over there right now. We don't have any. We have a few that are orbiting the sun, but they're facing the sun, and they wouldn't be able to give us data on L3 over there. So that's my pitch to you guys. We're going to take over the Earth by building millions of space shuttles to overtake the planet we're already on. I'm full of great ideas. Anyways, in summary, Lagrangian points are very cool. Make sure you check behind the sun for aliens. They exist when the gravitational force, centripetal force, and Coriolis force all add to 0, or cancel. And in order to find each of those points, we need to take the gradient and use the tactics that we have learned in this class. Lagrangian points, or I guess Lagrangians, calculating minimum and maxes and extrema and all of that, in order to find exactly the distance for where these points exist. This was a fun project. I actually really like this stuff.